Okay, so today we're going to talk about quantum chemistry. We will specifically talk about quantum numbers and the periodic table. So let's start first by defining the Schrodinger equation and seeing how this leads to the quantum numbers. The Schrodinger equation is in reality a combination of differential equations and linear algebra all in one equation, and it's rather complicated, especially if you start trying to solve for solutions of the wave function of the electron. But in a simplistic way, what the Schrodinger equation does is it basically correlates the distance from the nucleus to the electron, wherever it may be in the atom. And this coordinate system, which is the XYZ, the Cartesian coordinate system, basically tells you where the electron is at a given point in time from respect to the nucleus. Traditionally, though, and mathematically, it is best to define the position of the electron in respect to the nucleus not based on the Cartesian coordinates, but rather on spherical coordinates, in which you basically depict the distance from the nucleus to the electron as the radius of the atom, and you also determine the position of the vector, which basically tells you the direction of the electron in respect to the nucleus, with the angles theta and the angles phi. Now ultimately, we can see whether you're in the Cartesian coordinate system or the spherical coordinate system is that you have a function, a wave function to be more specific, where three parameters are present. You have radii for the electron or electrons present. You also have angles associated with the position of this distance vector. And so you actually have a multivariable function, a three multivariable function specifically. And so you could actually rewrite this as a combination of three individual functions themselves, one that contains only radius information, one that contains only theta information, and one where it only contains phi information. And multiplied together, they give you the overall wave function. This is a nifty trick of mathematics known as separation of variables, and it actually works out pretty well in differential equations. Now, we're not going to be dealing with the actual mathematics of it all, but suffice it to say that each one of these wave functions associated with either the radius or the angular components of the wave function lead to specific quantum numbers. So for all three of these different parameters in the wave function, we're going to have three different quantum numbers associated with the electron. And we're going to start first with the principal quantum number n. The principal quantum number n, which is associated with the radius of the wave function, or you could call it the radial wave function, is basically the same description that we have observed based on the Rydberg-Balmer equation. In fact, you get the same result just by looking at that aspect of the wave function. You have the charge of the electron to the fourth power multiplied by the mass of the electron divided by 8 times the permittivity constant square times Planck's constant square, and all multiplied by z squared over n squared. So this is exactly the same as the Bohr model. It doesn't really change. So you could still look at the atom and think of the atom in a way as having the concentric energy levels, energy level 1, 2, 3, 4, 5, 6, 7, and the electron can basically jump from each one of these energy levels. And as far as that description, there's no difference between the Schrodinger equation description of the electron interaction with the nucleus and that of the Bohr atom. But the difference is that now we're going to have some additional quantum numbers that will add complexity to the simplistic concentric picture that we have right here. Now, other thing that needs to be said, although we kind of have dealt with this already in the Bohr model of the atom, is that the principal quantum number n, which stands for the energy level of the atom, has to come in integral values. It can start at a number of 1, so that would be the lowest value you could have for n, but from thereafter you have to go up in values of 1, so you go from 1 to 2 to 3 to 4 etc., etc. So we've seen that already with the Rydberg-Balmer equation. Now the angular quantum number, this is something new that the Schrodinger equation actually brings into the picture. And this has to do with one of the angular components of the wave function, and it's given the symbol L, little l to be most exact. And what this is basically telling you as a number is how many nodes the wave function of the electron contains within itself. And if you think about a sphere, initially you could have a sphere and that particular sphere doesn't have any nodes. Because of that, the value of L will have to equal 0, meaning that it doesn't have any nodes. But we also do refer to this field as the s orbital. And in the remainder of the lecture, we're going to be referring to the locations of the electrons within orbitals, although I have something more to say in regards to that definition. If you do have one angular node present in your actual energy level, then what happens is that you take this s orbital and you simply squeeze it down the middle to create a nodal plane. Okay, so the nodal plane is shown right here. You can basically see. And another way to depict the nodal plane is by looking at the shading of the orbital itself. Notice that one area of the orbital has no shading whatsoever, but the opposite end, once you go past the node, has shading associated with the lobe. This particular orbital is known as the p orbital, and notice that the angular number 1 is associated with p orbitals. We're going to make use of this premise a little later in the lecture. Same thing for the s orbital. We have an L value of 0 associated with it. If you go ahead and create a second node by pinching on the p orbital even further to create a second node, you end up getting this Cloverfield these clovers or 4 petals that kind of look like even butterflies if you want to look at them that way. But basically what happens is that you have now this second node present in the orbital. You have one that's vertical and then one that's horizontal in this particular version. And because of that, you have this alternating shading to unshading to shading to unshading event happening throughout the orbital itself. The second thing to be said is that because this has 2 nodes in the orbital, the value of L equals 2. So d orbitals, which is what this particular one represents, is associated with an L value of 2. And the last one is regarded to as f orbitals. And the f orbitals are probably the most complex of the bunch because they have a total of 3 nodal planes. You have one vertical, you have one horizontal, and then you have one in-plane node present in this particular orbital. So you have 3 nodes associated with this wave, 3 angular nodes to be most exact. And so whenever you look at the number of L, if L is 0, you're talking about an s orbital. If L equals 2, you talk about a d orbital. If you have an f orbital, L has to equal 3. And if you have a p orbital, L has to equal 1. So this is something we're going to try to make use of when it comes down to the description of the electrons within multi-electron atoms. And another thing that I need to tell you right now, this is something that I hope you will memorize, is that there are restrictions associated with the quantum numbers. The principal quantum number, as long as it starts from 1, it can just go up to whatever value in integral numbers. But for the angular quantum number L, there are some restrictions. And the restrictions have to do with the value of the principal quantum number. As you can see, we can have a spherical orbital associated with the angular quantum number, and that means that the value of L could be 0. So that could be the lowest value of L that you could have. And you can go only up to a maximum that equals n minus 1. And the reason being is that you start with orbitals. You start with one orbital that has no nodes whatsoever, and after that you keep increasing the number of nodes from 0 to 1 to 2 to 3. So for whatever value of n you have, you will only have a total of n minus 1 nodes present in all of the orbitals combined. So that's the reason why you have this restriction present within it. But it is important to realize that as far as the value of L goes, you first need to know what the value of n equals before you make the restrictions for L. And as far as the values, you can start from 0 and you just move on to the higher value, just an integral number. So you go from 0 to 1 to 2 to 3 up to n minus 1, whatever that may be. All right, I'm going to stop the video at this point, and I will continue on the next video when we start talking about the magnetic quantum number.